lesson about a way to try to characterize correlations, not just in a non-locality scenario, but also in a contextuality one. So, in non-locality, the problem of how to characterize correlations has actually been widely studied. So, here we have, for instance, all possible principles that have been proposed, such as non-trivial communication complexity, no advantage for no-local computation, information causality, macroscopic locality, local analysis. So there are many principles that have been proposed to try to characterize quantum correlations. The problem is that all bad information causality here should be satisfied by almost quantum correlation, which is a superset of a set of quantum ones. And we have also some numerics that confirm that almost quantum correlations do satisfy the known protocols of information causality. So we know that what we have right now, it's not enough to get down to the quantum set. On the other hand, for contextuality scenarios, this thing has not been pretty much studied. So we know of at least one principle that has been proposed, consistent exclusivity, which proves not to be enough, but when you combine it with extra assumptions, you can actually get down to a set which is called Q1, that is the analog of the almost quantum correlations. So here we have different questions that we can ask. So for instance, which is the missing ingredient so that we actually recover the quantum set? And on the other hand, can we somehow formulate something to study these two phenomena at the same time? Because we have on the one hand non-locality and on the other contextuality, and basically you can somehow go from one to the other. So that's what we try to do in our paper. So how to propose principles to tackle these two things at the same time. So the key that we use to do this is the hypergraph formalism for contextuality. So I will briefly review that at the beginning of the talk and then move on to formulating the principle. So for contextuality scenarios here, well, basically what we have is a system that we can perform measurements on the system and obtain outcomes. And what we want to do is characterize which are the probabilities that describe the outcomes that we obtain when we perform the measurements. So in such a scenario, what we have is basically a set of measurements that we can perform on our system and a set of outcomes that we may obtain. And how do we study contextuality in such a setup? Well, what we do is we identify outcomes for different measurements. And it's such a device-independent approach, or this box type of picture. We do so when the events happen with the same probability. So if we have two different events of an outcome, so by event here I mean an outcome given an input, whenever those two things happen at with the same probability, we identify them as the same event. For instance, from a quantum point of view, this identification happens when you have two different measurements. So take, for instance, as an example, two projective measurements. And there are two outcomes that have associated the same projector. So you know that those two things actually correspond to the same event, and that whatever the underlying state is, they will always happen with the same probability. So basically that's the idea underlying this identification of outcomes. So within this framework, what we say is that measurements actually share outcomes. So the fact that measurements are allowed to share outcomes is the way that contextuality arises. So from a pictorial point of view, contextuality scenarios are depicted in a hypergraph. So here, the dots, the vertices, are the events, so outcomes in measurements, and the hyperedges denote the set of outcomes that correspond to a complete measurement. And what we do, or what we want to do, is to understand the allowed probability distributions within such a hypergraph. So why to use a hypergraph goes beyond the scope of the talk, so I'll skip that and move on to give here some examples of different definitions of probabilistic models that we might be interested in. So, for instance, given a hypergraph, we can have the general probabilistic model, so which is the most general thing that we can do, well, we can assign probabilities to the events such that they sum up to 1 whenever they correspond to a hyperedge. Also, we can think of classical models. So, classical models are those which are just linear combinations of deterministic models, basically assignments of zeros of ones to the corresponding vertices. And finally, we have quantum models, which are those which may arise by assigning projectors to each of the vertices such that they sum up to the identity in the Hilbert space, and such that there exists a quantum state that together they recover the assignment of probabilities to the vertices. So those are some examples of sets of probability distributions that may arise in such a contextuality scenario, and here is a picture of the way the different forms that these sets may have. And here the fact that the quantum set is slightly larger than the classical set is what evidences contextuality. So now that we have kind of a picture of what we mean by these contextuality scenarios, let's move on to the formulation of the principle. So here what I've been talking so far is a kind of a microscopic scenario where we have a system and we perform measurements and obtain outcomes. So from a pictorial point of view, we can think of it as a realization. So we have a source. This source produces a system and sends it to a measurement device. This box here represents the measurement device, which actually sends then the particle to different detectors depending on which was the outcome of the measurement. So this is like a microscopic version of the setup. So the way that we understand the microscopic limit here is basically a source that produces not one but a number n of systems, sends them to the measurement device, and that what we have is different number of systems that click in each of the detectors. So this is like a macroscopic version of this microscopic scenario. So here what we have is this probability distribution that I was telling you about. So these probabilities that each of the events happen. So here by V, of course, I denote outcomes given measurements. But here we don't have that anymore. What we have instead is a distribution of intensities in each of the detectors, and what we have is a distribution, a related distribution of the those intensities. So now, and of course, the distribution over those intensities will depend on what is the underlying microscopic model for the scenario. So now, the macroscopic non-contextuality principle basically says that this microscopic probability distribution, in the limit when we have a microscopic number of systems entering the measurement device, should have a non-contextual explanation. So basically it's that at the limit of an infinite number of parties entering the device, somehow the contextuality should average out. So that's what we mean by macroscopic non-contextuality. Formally, let me just try to go quickly through the argument. Let's see how these macro and micro scenarios relate. So consider a random variable, d, which gives you a value of 1 whenever outcome v happens for measurement e for the eth particle. And by doing so, we can see the deviation of the mean intensity in this way. So which are the properties that this object here now satisfies? Well, first, it has a normalization, so it has to sum up to 0 whenever you sum over all the vertices of the hyperedge, so meaning all the outcomes of the measurement. On the other hand, the central limit theorem tells us that whenever we have a macroscopic number of particles entering the measurement device, the distribution over this variable here is a Gaussian. So, and by relating it to the original microscopic probability distribution, you can see that the corresponding moment matrix associated, for instance, to measurement E for these two outputs relates to the original probability distribution in this way. And finally, the constraint arising from macroscopic non-contextuality means that when we have a macroscopic number of systems entering the measurement device, the distribution over the intensities for all outcomes should be described by non-contextual probability distribution. So there exists a joint probability distribution that tells you the probability for each of the outcomes. And the way that you recover for each of the sets the experimental probabilities that you might measure is basically by tracing out the outcomes that do not appear in that hyperage. So if we take this form for probabilities of the intensities, we can also compute a moment matrix of this variable here. And what you can see is that such a matrix satisfies these properties, so basically it satisfies this normalization constraint and is positive semi-definite. And moreover, when U and V belong to the same measurement, they have to equal this moment matrix here. So now we have a proper definition of when a microscopic probability distribution satisfies the macroscopic non-contextuality principle, which is the following. So you have a microscopic probabilistic model that is a valid assignment in your contextuality scenario, and you say that it satisfies macroscopic non-contextuality whenever there exists such a positive semi-definite matrix that satisfies the three constraints that I previously explained. So now the thing is to relate this definition with the definition of Q1 models. So in the hypergraph formalism, we see that the probability distribution belongs to this set whenever there exists a positive semi-definite matrix that satisfies these constraints. So we can actually see the relation between the two definitions here. And by doing an appropriate identification of the gamma and the M matrices, we can see that P satisfies macroscopic non-contextuality if and only if it belongs to the Q1 set. So this set here is slightly larger than the set of quantum correlations. So basically, by this, what we prove is that such a macroscopic extension of the experiment actually allows you to go down to a set which is slightly larger than the quantum one. So how do we relate this now to Bell scenarios? Because so far I've only spoken in general about contextuality. So let's take a step further and see what happens with Bell scenarios. So in Bell scenarios, what we have is a set of n parties that they can perform measurements and obtain outcomes, and they are space-like separated. And the condition of probability distribution that we're interested in is actually in this form. So now, in this hypergraph formalism, what we do is we think of these n parties such as one big system that performs measurement X that has information about the individual measurements that the parties perform, and an outcome A that is the collection of all the outcomes that the parties obtain. So here is a way of thinking of this probability distribution as one in the contextuality scenario. And it's also been proven that there exists a way of writing a hypergraph for such a Bell scenario where we have not only the simultaneous measurements by Alice and Bo, but also extra hyperedges in the description that are actually ways to enforce the known signaling constraint. So if you write a hypergraph like this, basically what you have is that the set of general probabilistic models as such possible in such scenario is actually the set of no signaling correlations. And the same happens with the set of classical and quantum correlations. And so here, basically, what was proven is that a probability distribution in a Bell scenario is almost quantum if and only if it belongs to the Q1 set of the corresponding hypergraph. So here we have two concepts. We have a non-locality scenario with a probability that belongs to the almost quantum set. On the other one, a probabilistic model that belongs to the Q1 set of the corresponding hypergraph, and now we see a Bell scenario as the contextuality one. And here, then, what we can do is make a link between almost quantumness and macroscopic non-contextuality. So we can say that a probability distribution P is almost quantum if and only if it is macroscopic non-contextual in the corresponding Bell hypergraph. So basically what we were able to do is to characterize this blue line here, which is a set of almost quantum correlations. So, yeah, I think we're running time. So, to conclude, what we did is to generalize macroscopic locality, which was an original principle proposed by Belen-Sainz, to contextuality scenarios. So, the original macroscopic locality was only formulated for bipartite Bell scenarios, and it basically recovered a set that was larger than the almost quantum one. It was the first level of the MPI hierarchy for those of you who are familiar with that. So basically we have found a way to take that principle, generalize it to contextuality scenarios, and recover by this generalization not only almost quantum probabilistic models in general contextuality scenarios, but also to get a little bit closer to the quantum set and get down to almost quantum correlations. So we also see that the way that to strengthen macroscopic locality in Bell scenarios was actually by considering these correlated measurements, which were these extra hyper edges in the hypergraph that enforce the no signaling principle. So that's basically the main ingredient that we add somehow, we managed to add to the macroscopic locality principle to make it stronger and get down to almost quantum correlations. So now, this principle that we propose fully characterizes almost quantum models, not just in contextuality scenario, but also in multipartite Bell scenarios, which is something that hadn't been done yet. So, and it doesn't require any extra assumptions. So that's, I think, that the main result that we have. And as I said, it directly applies to multipartite Bell scenarios. And as the open problem that we still have is now how to go from almost quantum to quantum. So how to, and we think that the way to do it is to try to now consider sequences of measurements in these scenarios, not just single measurement and outcome, but starting to consider sequences of that. The reason why we believe that is because there was a previous attempt by Belen-Sainz to generalize macroscopic locality to contextuality scenarios, but instead of working in the hypergraph formalism, he was considering observables that can be jointly measured with different other observables in different contexts. And the problem that he found there is that he had to consider sequences of measurements because of all those observables in the same context. And that somehow is not actually well defined within almost quantum correlations. So almost quantum correlations are just a measure and obtain, and not, in the definition you cannot actually deal with sequences of things. So we believe that and actually he couldn't make that work. So within his attempt to try to generalize the principle, he couldn't even prove that almost quantum correlations would actually satisfy or not this intended generalization. So we believe that by trying to make that a formal statement, we might perhaps find a way to get, perhaps not to the quantum set, but at least with something which is smaller than the almost quantum set. So that's it. Thank you.
Thanks so much. Question at the end.
Sorry. It's not so much a question as a question. So again, remind me, what is the definition of almost quantum model? I somehow...
Oh, there are many definitions of the almost quantum model. This is the one that I chose to present because of the relation to the macroscopic contextuality principles, but there are many other definitions.
This is the definition of this Q.
Yeah, this is one of the definitions of the Q1 models. Another definition that perhaps will be more intuitive and that I like better is, so here for the quantum models we have a Hilbert space, a state, and projectors that sum up to the identity and recover the probabilities. So for the almost quantum models, instead of having here an inequality, what you have is less than or equal to the identity. So basically your projectors are not normalized in the Hilbert space. Yeah, they are normalized as far as the state is concerned because the probabilities should be normalized. But perhaps you need these extra dimensions in your given space to ensure the orthogonality of the properties.
Other question?
How is that related to the fact that in principle you can also violate contextuality inequalities with classical inequalities, microwaves for instance?
I'm sorry, I didn't.
So people have done experiments where they violated some contextuality inequalities with microwaves, with classical fields. So is it then this the Gaussian assumption that you have, is it not fulfilled, or?
It might be, yeah, because we are assuming that when you have microscopic things, microscopic contextuality is averaged out. But I was not aware of this experiment, so I do not see how how they relate. So perhaps you can tell me later the
Yes,
references
yes.
so that I can take a look at it. Thanks.
Another question?
Yes.
So I assume it's just a matter of example that you're not thinking about POVMs in the quantum case.
Well, we are not thinking about POVMs because POVMs actually are not included in this hypergraph formalism for contextuality. So the formalism doesn't include POVMs in the same way that it doesn't include, it doesn't deal with underdeterminism. So when you have, we have here, so classical models are defined in a deterministic way. So, and at the same footage, quantum models are defined with projective measurements. So that's why we are not considering POVMs when also studying or formulating actually the.
They're just not interesting for this.
Sorry?
They're just not interesting in this particular setting.
It's not that they are not interesting, but here, I mean, you can formulate. You can see what happens when you now formulate POVM quantum models, but you can formulate that in such a formalism, but it's not clear which are the type of constraints that we can learn from it. So basically, if you now allow these things to be POVM elements instead of projectors, you could actually realize things here outside this green set. But you could actually do the same thing by allowing your classical models to be non-deterministic. So it's not really clear how to deal with those two sets of correlations in this ring.
Okay, thanks very much. Let's thank Anna again.